Hello, everyone, and welcome to the Basics of Compound Interest Part 2. So there's going to be three parts to the basics of compound interest. And then after that, we'll just dive into annuities. So what I want to talk about now is the realistic situation of you make an initial deposit into an account, and then you make afterwards multiple deposits or multiple withdrawals. Okay? And there's really two ways to handle this very practical situation. There's the rather inefficient method of finding the balance after every transaction. And my experience is that quite a few people in this course actually do this method even, towards the end of the semester. They stick to this method. In real life, it's a very inefficient and not very useful method because, for example, if you're a landlord and you take in rent every month and you deposit into an account, 20 years, after 20 years, that's going to be 250 deposits. If you're doing calculations involving that, do you really want to do 250 and do you want to really find the balance after every single month, 240 times? I think I said 250. I don't know why I said that, but anyway. And the answer is probably not. Okay. The other method is to accumulate each transaction and sum. And what do I mean by that? Well, particularly here, I mean withdrawals count as negative money. So both deposits and withdrawals, in this sense, accrue interest. Okay, and it makes sense to treat negative money as accruing interest because, or rather, it makes sense to think of withdrawals as accruing interest. The negative money that was withdrawn, or the negative money the withdrawal that counts as negative money accrues interest. And the reason why is that if you did not withdraw that money, then the extra money that you that would have been in your account obviously will accrue interest. So any money that you withdraw, you really have to think, hey, wait a minute, if I withdraw that's money that could have been accruing interest. That's a very important general principle and very important way of thinking in just general, if you open up a business or in any financial situation, that when you withdraw money, really that is money that could be accruing interest. All right. And in B, often time diagrams are useful. And I'm going to stress time diagrams throughout this course. They are just incredibly useful. And a time diagram is really just a diagram that illustrates when each transaction is made and how it accumulates interest. That's really all a time diagram is. So let's just dive into an example. I have an account that earns 7% effective annual interest, $1,000 initial deposit. Let's say $500 is withdrawn 6 months after my initial deposit. 1 year after my initial deposit, I deposit 250 more. And 2 years after my initial deposit, I withdraw $100. And finally, 3 years after my initial deposit, $200 is deposited. Find the balance after 3 years using both methods. And I'm just going to do really both of these methods, these two methods, to illustrate that you get the same answer. All right. Okay. So what's the first method? Well, so we have an initial deposit of $1,000. Okay. And let's ask the question, well, how much do we have after 6 months? Okay, well, it's not very subtle. The $1,000 accrues 6 months of interest. to become 1,001.07 to the 1/2. Remember, we have 7% effective annual interest, so 6 months corresponds to t equals 1/2 of a year. Okay. So we take that amount, that's how much the 1,000 becomes after 6 months, 1,001.07 to the 1/2, but we withdraw $500. So we just dump this here into a calculator, and you get roughly $534.41. Okay. Okay, so 6 months later, or 1 full year after my initial deposit, what happens? This $534 and roughly 41 cents itself accrues half of year interest. Okay, and after it's done accruing this half of year of interest, you deposit $250 for a grand total of $802 and roughly 80 cents. Okay. So after 1 more year, or after 2 full years after the initial deposit, it's the same game. This $802 and roughly 80 cents accrues 1 year of interest. But at the end of that year, you withdraw rather $100 to get $758 and roughly 99 cents. And last but not least, after 1 more year, or after 3 full years after the initial deposit, the $758.99 roughly accrues 1 year of interest to become $758 roughly 99 cents times 1.07 to the 1. It's a bit silly to write to the 1, but I'm just writing it to emphasize t equals 1, 1 year of interest. And then finally, after 3 years, you deposit $200 for a grand total of $1,012.12. Okay, so even with only a couple of transactions, you can see this really becomes quite a pain in the ass pretty quickly. Right? And I mean, if you really want to do this method in this course, I can't argue that, I guess, but this is really not a method that's useful, particularly for Exam FM, and you're not going to really do well in Exam FM if you're glued to this kind of method. Okay, so let's do this, the other method, method B. So let me first draw a time diagram, and you don't always have to draw a time diagram. For this example, I personally maybe wouldn't draw a time diagram, me personally, but if you're ever a little confused as to, exactly what's going on in terms of what accumulates how much time of interest, just draw a time diagram. Okay, so anyway, what is a time diagram? I have to make this a little smaller. Give me 1 second. That's a little better. Move this over. Actually, I'll make it a little. Let's make it 125. Oops. All right, sorry for that. Okay, so, right, so we have an initial deposit of 1,000, okay? And so we're basically just going to accrue every single withdrawal and deposit by the amount of time it sits in the bank. So this sits in the bank or in the account for 3 years. So this 1,000 accrues 3 years of interest. It becomes 1,001.07 to the power of 3. Okay. After 6 months, or when t equals 0.5, where t is in years, we make a $500 withdrawal. So that accrues 2.5 years of interest to become minus 500 times 1.07 to the 2.5. And again, one way of thinking about it is, if you didn't make that $500 withdrawal, then that's $500 extra money that you would have that itself would accrue 2.5 years of interest at 7% effective annual interest. Okay, so we just keep playing this game. After 1 year, we make a $250 deposit that accrues 2 years of interest. And after 2 years, we make another, or rather, we make a $100 withdrawal that accrues 1 year of interest. Last but not least, at the very end, we make a $200 deposit, and you add all these up. Remembering this is a minus sign here, and this is a minus sign here. You get the same answer, $1,012.12. Okay. So again, me personally, if I was given this as a problem, I would probably just, do 1,000, 1.07 cubed minus 500, 1.07 to 2.5, plus 250, 1.07 squared, et cetera, just dump it into the calculator. But anyway. Okay. So if you're really not convinced as to why withdrawals should accrue interest, let's just do a very, very simple example that should illustrate this. Let's just look at two scenarios, two very, very simple scenarios. Let's say scenario one, a person invests $5,000 at 8% effective annual interest and waits 6 years. And let's say a person essentially immediately makes a $1,000 withdrawal. So that's the effect of really only investing $4,000 at 8% and wait 6 years. But I'm kind of thinking, well, you initially invest $5,000 and immediately withdraw $1,000. Okay. Again, one perspective is that with that $1,000 that you've withdrew, that is money that would ordinarily sit in the account for 6 years and accrue interest. So let's just see exactly that at work. So in the first outcome, you have roughly $7,934.37. And in the second outcome, and of course, it's just 5,001.08 to the sixth, nothing very subtle there. And the second outcome is 4,000 times 1.08 to the sixth. That's 6,347.49. So the difference is most emphatically not $1,000. It's quite a bit more than $1,000. It's $1,586.87. Okay. Right. So the point is that if you did not make that initial withdrawal of $1,000, you would have exactly $1,586.80 more than you would if you did make that initial withdrawal. So really, to get the correct answer, you take, the original investment without the withdrawal, and then subtract the withdrawal, accumulating 6 years of interest. And if you do exactly that, take outcome one minus this 1586.87, you're obviously going to get outcome two. I mean, all you're doing is 5,000 times 1.08 to the sixth minus 1,000 1.08 to the sixth gives you 4,000 1.08 to the sixth. Okay. So hopefully that makes sense. I mean, this is conceptually maybe a little bit tricky. I mean, in some sense, I think conceptually this concept is maybe one of the trickier parts of the course, kind of why withdrawals should accrue interest when you count it as, negative money. But anyway, hopefully this makes sense. Okay, so let me do another example, and we'll do examples like this throughout the course. So we have an initial deposit of $200. an interest account rate of 8% effective annual interest. So you have only one deposit, and that's at the end of the second year. You make, withdrawals of $100 after 6 months and 18 months, and there's a withdrawal penalty of 2% of each withdrawal amount. Find the amount in the fund after 2 years. All right. So let's get rid of all this. Okay, so I'm going to draw a time diagram here. Make this a little bigger. That's good enough. Okay, so I have an initial deposit of $200. At the end of 2 years, that accrues 2 years of interest, so that becomes 200, 1.08 squared. Okay, so I'm withdrawing $100 after 6 months, which in years is 0.5 years, of course, like last time. So that's going to be minus 100 at p equals 0.5, but we also have the 2% penalty on the withdrawal amount. Obviously, 2% of 100 is, well, 100 times 0.02 is just 2. So really, this is like a minus 102, or really it's like a $102 withdrawal. Okay, and that withdrawal accrues 1.5 years of interest. So it's minus 102 times 1.08 to the 1.5. So we after 18 months, we make another $100 withdrawal. 18 months corresponds to a year and a half. So same kind of deal. You think of that, the withdrawal plus the penalty, as a deposit of a withdrawal of $102. Definitely not a deposit. And we're looking at the end of 2 years. So 18 months to 2 years is 6 months of interest. So that's 0.5 years of interest. So this minus 102 accrues 0.5 years of interest at effective annual interest rate 8%. Right, so again, you add all this up, being mindful that this is negative and this is negative. So you take this minus this plus the 150, and you get 162.80. And if you so desire, you can check using kind of method A that you get the same answer. Depending on how you round off, you might be off by like a penny or so. That's okay. All right, so let me talk very briefly about simple interest. So the idea of simple interest is that, so if we're dealing with a fraction of a year, or particularly if we're dealing with financial transactions that occur at microseconds, it doesn't really make sense to use compound interest, and compound interest is just too complicated to really do all these little tiny, transactions at, tiny little milliseconds or whatever fraction of a, tiny fraction of a year we're doing with. So we need a kind of concept of interest that's, no pun intended, a little simpler. And that is not subtly called simple interest. And that's exactly why it's called simple interest. It's just simpler than compound interest, and hence it's more effective when dealing with fractions of a year, particularly small fractions of a year. Whereas this is very, very, very unrealistic when, for, any time longer than a fraction of a year. So the idea of simple interest is, again, no pun intended, very simple. We say an account earns simple interest at interest rate I as a decimal if the accumulation function is just your initial deposit times 1 plus IT, where T is in years. Okay, so as a very simple example, this is basically just plug and chug. There's not a whole lot to this. Let's say you take out a 90-day loan of $50. is made at 15% simple annual interest by the amount due after 90 days. Okay, so all we're looking at is we're trying to see what this $500 accrues to using simple interest after 90 days. And just like before, T is in years, so we got to convert 90 days as a fraction to it, rather, a fraction of a year. Okay, so let's do that. So, of course, as I mentioned in the last video, we treat a year as 365 days, keep things nice and easy. Okay, so just plug and chug. T is 90 over 365. I, 15% as a decimal is 0.15, so it's 500. 1 plus 0.15 times 90 over 365. And that's 518.49. Okay. All right, so let me do a much more interesting problem and something much more akin to something I would give on a quiz or exam. And maybe you would see something like this on Exam FM. Not sure if you would actually, but it's still, you know, at least at the level of challenging. It's like at the challenge level of the Exam FM. Okay. And sorry, I should also mention that unless otherwise stated, we're going to assume compound interest. Compound interest is used much more often than simple interest. And like I said, simple interest is particularly used for small fractions of a year. So unless otherwise stated, we're using compound interest. Okay, so the last example I want to do in this video is as follows. A person invests $1,000 and withdraws all the money from this account once the investment fund or whatever hits $3,000. Effective annual interest is 7%. And for full years that the money is in the account, interest is compounded annually. So it's particularly compound interest, but for fractions of years that the money is in the account, simple interest is used. Okay. So the point, so the idea here is that, you know, money sits in this account for a certain number of full years, and it accrues compound interest for all those years, and then it sits in the account for some fraction of a year, and for that fraction of a year, that, you know, the amount earned in the account earns simple interest. Okay. When exactly does the person withdraw all the money? Okay. So we're going to employ, I don't know if I'd call it a trick, but the idea of this problem we're going to use every now and then throughout this course. So it's a good problem for only that reason. Okay, so the idea is I want to first find the number of full years before withdrawal. I'm not really initially concerned. Well, I mean, we're going to need to find out after those full years, the fraction of time that money is going to sit in the account. But we first need to find the number of full years before withdrawal. And the way we do that is because for full years, interest is compound and it's 7% effective annual interest. We're just going to set this up as if for the whole entire time until withdrawal, we have compound interest. Okay, so we divide both sides by 1,000. So this should be a T here. If it's not clear, make that nice and red. Okay, so it's 1.07 raised to the T equals 3. Of course, we take ln of both sides. ln drops the T. So it's T is going to be ln of 3 over ln of 1.07. That's 16.24. So what this tells me is that we have 16 full years. That's the amount of time money sits in the account. That's the amount of full number of full years that money sits in the account. Okay? Anything more, which the next one would be 17 years, would give you, based on this analysis here, more than 3,000. Because, well, 1,000, 1.07 to the t is obviously an increasing function. And if you don't believe me, well, just check yourself. If we let money sit in this account for another full year after 16 years, but just 17 years, then we would have 3,000. This would be $3,158.82. That's a typo here. Sorry about that. Doesn't really make sense. But anyway, it's get rid of that here. Sorry about that. So regardless of exactly what it is, it's well over 3,000, and this person withdraws the money after exactly rather when the account has $3,000. Okay, so the money sits for 16 years. Okay, and after 16 years, how much do we have? Well, just 1,000, 1.07 to the 16 is $2,952 and roughly 16 cents. So let's say S is the time in years after 16 years. Okay, so after 16 years, this is exactly how much we have. That sits in this account and earns 7% simple interest for S years. Okay. So we just solve for S, just plug into the formula for simple interest, and we're treating this as if this is kind of our initial deposit, so to speak. We're kind of resetting the problem, and that's something we'll do also quite often in this course. Kind of, at a certain time, we'll reset the problem. A good example of that would be refinancing a mortgage. It's essentially you're almost resetting a mortgage when you do that. As I said before, we'll spend some time on refinancing and do problems determining at what interest rate is it worthwhile to, or rather, is it worthwhile to refinance or not? What interest rate do you need to get a refinance loan with monthly payments that you want, et cetera, et cetera. Anyway, I really like those problems, so that's why I sometimes ramble about them. Okay, so anyway, we solve for S. This is very easy. Just divide everything by 2952.16375. Subtract 1, divide by 0.07. I'll trust that you can solve for S very easily. And if you do that, you get 0.23148. So the final answer is the money is withdrawn after 16.23 years, which is roughly 16 years and 3 months. 0.23 is roughly 0.25 is 1/4 of a year is 3 months. Okay, so I'm going to basically end there. And what I'll discuss in the next video is the very, very, very important topic of present value. Okay. So yeah. All right. So hopefully that made sense. And again, please come to my Zoom office hours if you have any questions, or send me an email. Homework will be up soon. And so long. Stay safe. Take care. And new videos will come pretty soon.